Cool. Hi, everybody. We're doing topic 25 and kind of 26 today, which is logistic regression as well as evaluating classification models. But a couple reminders to start. First, try to get your blogs done this week. It's really going to ramp up. Our material is really going to ramp up towards the end of this week. So if you can get your blog done and submit it on phase 2, sooner the better. So I'll be checking for those submissions starting next week. I saw a couple people have already submitted those, so thank you very much for doing so. But try and get it done by this week. If anyone's stuck with ideas, let me know. Happy to talk about it. Also, if you take a look at the calendar, this Friday, which is really soon, I'm going to be introducing the next project. Now, it seems to be pretty soon because we're only like halfway through, or I guess we would be like 2 weeks in to the phase by that time. But I'll be introducing the phase 3 project then. On Slack, I put a little message there for you to vote whether you want to work solo or in a pair. So I'm giving you a choice for this project. By default, I'll put you in a pair, but I mean, it's just really up to you whether you're going to work on this one solo. Because phase 4 project is also going to be paired, and then the last project, well, is your capstone, so it's going to be your own as well. So please indicate if you want to work on this project on your own, especially. So yeah, other than that, I did mention that this week I'm going to be giving everybody a little coding assignment. Now that I will start alluding to today, but I won't give you like that assignment until the end of the week. So just letting y'all know to look out for that. Cool. Any questions before we start diving into new material? All right, well, today we're going to hit a brand new model called Logistic Regression, as well as how to evaluate all of these new groups of models. But before that, I really want to scope out what we're doing in the context of data science. So here is a mind map. Is this considered a mind map? Yeah, I think this is a mind map. But here's a mind map that is basically an overview of machine learning. And I do want to talk through these different arms and what we've hit so far and what's up ahead, just so we have better context of what we're doing fits into the greater picture of like machine learning. So what have we done so far? So far what we've done is supervised learning regression. Now, supervised learning has regression and classification. Spoiler alert, all of the models that we're going to be doing this week and next week are all classification models. Most of them do have regression counterparts, and I'll talk about that when we get to those models as well. But our last project was regression. The idea of supervised learning is that we are trying to predict something. It's either going to be a continuous variable or a categorical variable. So for phase 2, we were doing predicting a continuous variable, therefore regression. And for this upcoming project, we will be predicting a categorical variable, so therefore classification. So some examples of regression, I mean, this should make sense to you all already. Popularity prediction for advertising, forecasting weather, market, estimating life expectancy, population growth prediction. These are all continuous outcomes, so therefore they all fall under regression. Now, this phase, we're going to be mainly talking about classification. So examples of that, identity fraud detection. So fraud detection is actually a really big one. One of the project's data sets is, not actually predicting fraud, but there are some really popular data sets that are on Kaggle that you can choose to use if you want to get into fraud detection. I will say that fraud detection is really big, especially in like the finance industry. Credit card fraud is one of the bigger applications of classification in finance. Also, there's customer retention. Now, this is the one where one of our data sets is on customer retention. There is one data set for this project that is provided that predicts whether a customer churns or not. So basically customer retention. I believe the data set's for a telco or something like that. Diagnostics, if you want to I'm guessing this may be on like diagnosing something, whether it is a feature of whatever the data is, but also it can be detecting things like in detecting disease, for example. That's actually a very common data set as well. And then next phase, we'll get into image classification, because for this phase for now, we're still going to remain with our numerical data, but classification does expand to image data. You can also expand to text data. You can actually apply all of the models that we're going to be talking about this week and next week to images and text as well. But how we deal with image and text data, we'll talk about next phase. Cool. So that's supervised learning, which is going to be basically the rest of this phase. Now, unsupervised learning, which is this blue arm over here, is what the beginning of next phase is going to be. So just as a sneak preview, what we're going to hit, we're actually going to talk about both dimensionality reduction and clustering. Just an example of what unsupervised learning is, and I will talk about what unsupervised learning is when we get to that as well. But the whole idea of unsupervised learning is you're not really predicting an outcome. You're really doing things that don't really have a label. So what I mean by that is clustering. So if you think about clustering, one common use of clustering is in sports. So for example, I don't know too much about what people are saying about sports nowadays, but I know that in in basketball, for example, there are like 5 positions on the court, right? And there are a lot of clustering algorithms being applied. There are a lot of clustering algorithms being applied onto basketball players to try and group them into different groups that maybe do not align with the 5 positions on the court. So that's an example of unsupervised learning. We'll get way more into that next phase. Dimensionality reduction is a little complicated for now, but we'll talk about that next phase as well. I do want to point out that reinforcement learning, which is basically how they teach machines to play chess and all those other board games, we will not get to reinforcement learning in this course. I will say it's like a common next step if you're really, really interested in like AI and as well as like deep learning, as well as how gradient descent and algorithms work. If you're really interested in that component, then I do recommend, and I'll give you all some resources at the end of the course about reinforcement learning, but we actually will not hit that. I actually myself don't have much experience in reinforcement learning either. So hopefully with that, we have a bigger context or a better idea of what we're doing in the greater context of machine learning. Thoughts, questions? Hopefully that like helped to set the scope a little better. Okay, cool. So as I alluded to, all of the algorithms that we're going to be talking about this week and next are going to be classification algorithms. So the first classification algorithm we're going to talk about is actually very, very directly related to our linear regression, and it's called logistic regression. So there are a lot of words here, but I'm going to go through all of these. So logistic regression is extremely, extremely similar to linear regression in the sense that you are looking for linear relationships between your features, as well as coefficients are some of your outcomes that you're going to use to produce your analysis. So we'll talk about those later as well. Different from linear regression, it predicts probabilities associated with a success or a failure, or any sort of categorical outcome. Examples of categorical outcomes is an email spam. What is the probability that a citizen will vote Republican? Is a homeowner likely to default? Is a person going to buy a product? So on and so forth. So very, very similar to linear regression, we also have assumptions for logistic regression, although they're slightly different. So first, the dependent variable is required to be binary. Now, you'll see in the example I have later on, it is not just it mathematically works on a binary outcome, but I'll talk more about how it expands into more categories. So if you needed to predict like one of 5 different categories, it can still do that. But I'll talk about what the implication of that is in a little bit. Similar to linear regression, you only want to have meaningful variables. You can also get that p-value output. Stats models also has a logistic regression model summary output as well. So you can check for significance there. Also, independent variables should be independent of each other. So the multicollinearity assumption, that is also something that holds for logistic regression. One that's slightly different is that the linearity assumption is slightly changed. So rather than your target being linearly related to each of your features, you need each of your features to be linearly related to the log odds. And I'll talk about log odds in a little bit. But now, because our target is no longer a continuous variable, rather it's like a 0 or 1 outcome or 2 classes, you need it to be linearly related to the log odds. And log odds I'll talk about in a little bit too. Another assumption is logistic regression usually does require large sample sizes. It's kind of related to how the gradient descent works for logistic regression. It has to do with maximum likelihood estimation, if anyone remembers that from the middle of phase 2. But it does require large sample sizes, not to say that you can't apply a logistic regression on a small data set. It just maybe won't perform as well as some other models we'll talk about later this phase. So some key differences, like I mentioned before, the difference in the linearity assumption, it is not a linear relationship between dependent and independent variables, because your dependent variable is just a 0 and a 1. It's going to be very hard to get a linear relationship between the two there. But it does assume a linear relationship between the link function and independent variables in a logit model. And I'll talk about that transformation in a little bit too. Next, the dependent variable does not need to be normally distributed, which makes sense, right? If your dependent variable is just a bunch of categories, can't really be normally distributed. So it does not use OLS for parameter estimation. Instead, it uses MLE. So the gradient descent that is being done on the cost function is actually an MLE equation, which we actually don't have to go through because it is pretty in-depth. However, I do link some videos if anyone is interested in breaking down how that process works. It's actually kind of interesting. But yeah, instead of doing an OLS calculating the distance between the points and the line and then just, solving for that, minimizing that cost function, you're using MLE to find the best fit of the curve to your data. Very similar to, I don't know if anyone remembers my puppy weights example. You're trying to fit the best curve to your data. Next, your errors need to be independent but not normally distributed. So what that means is, if you remember at the end of our modeling, when we check for our normality assumptions, that doesn't really that's not an assumption for logistic regression, just to keep in mind, because again, your errors are going to be zeros and ones, because your error will be 0 if it's correctly predicted, 1 if it's incorrectly predicted. Okay, that was a lot of information prefacing logistic regression. Any questions at this point? Awesome. Okay. So logistic regression has this equation. I think it's easiest to start here. So let's just say that for logistic regression, our outcome is 0 and 1. So let me grab my annotator. So when we are making some sort of prediction, our actual values are actually going to be along the 0 and 1 line. So this is our y-axis, the vertical is our y-axis, and all our data points are going to be along either 0 or either 1. That's just the nature of categorical variables. You're not going to have any points here because you can't have half a category. So let's undo that. So the idea of logistic regression is, let's just say we want to fit a best fit line through these two rows of points. And that's this blue line over here. You're going to fit this linear model to this to these points. And of course, you're not going to get very, very good R-squared because everything is either a 0 or 1. You're going to have a lot of error. Like, for example, any point that isn't far away enough is going to have a pretty great error. You can see that these points are going to have pretty large errors. These points out here are going to have pretty large errors. So the idea of logistic regression is you first imagine you're fitting a straight line through there. So fitting a straight line through there is going to get you this equation here, a linear predictor, your linear predictor equation, which is literally your linear regression predictor. You can see here we have our intercept term as well as our parameter terms and our x terms. After which, to just make your line fit your data points better, you're just going to do a transformation of your y variables. So you can see here, oops, if I scroll, everything moves. Let me just delete everything for a bit. All right, so if we have this transformation here, since we know that all of our data points are going to be either 0 or 1, you can interpret any prediction that falls in the middle as a probability of it being 1. So for example, off of this linear model line, let's just say that, let me draw back in all of those things. There we go, and let me scroll so that it fits again. Cool. All right, so let's just say that we have a prediction for this data point over here. this data point here is going to have, I don't know, let's just say an estimated y value of 0.3, because roughly it looks like it might be at around 0.3 there. So if that point there has an estimation of 0.3, is it closer to 0 or 1? So you can sort of think of it as some sort of threshold. If it doesn't pass, let's say the 0.5 threshold, we'll just round it down to 0. And anything that gets like a prediction that's up here, let's just say that it's up here, closer to 1, we'll round it up to 1. So you can sort of think of these predictions that are in the middle as probabilities, which is what logistic regression does as well. So with that, since we know that all of our values are going to sort of be between 0 and 1, what if you have a prediction that ends up being out here, right? Out here. These are going to make a lot less sense. So therefore, we're going to do what's known as a sigmoid transformation to force all of our values to be between 0 and 1. Sort of like when you're scaling your values. However, it doesn't scale it in a linear fashion. It scales it such that it always has this like S-shaped curve. So anytime you see a curve like this, it's just called a sigmoid curve. So the idea of doing this transformation is if you have, predictions along this line, it's going to take this blue line and basically force it into the orange curve. So all of your predictions are going to be within 0 and 1, and anything that is between 0 and 1 will just be rounded off to either 0 or 1, and that's how you get your binary output. So mathematically, what's happening there is you're doing this transformation. Your predicted y is going to be 1 over 1 plus e to the power of your linear equation. And so if you want to get your prediction, you just first get your linear model and then plug in all of your parameter values as well as your variable values, and you can get a number between 0 and 1. And based on what it is, you round it off to 0 or 1 to make your classification. Questions about that? I recognize that there is a lot of information here. Cool. Now, you only have these beta values after the gradient descent process is done. So the gradient descent process, I'm not really going to go through because it is pretty complicated. But again, I linked a couple of videos at the bottom of this notebook for you to check out if you're interested in figuring out how the gradient descent procedure is done. Okay, so let's take a look at a couple examples. So let's just say that I am building a model to predict whether a plant is poisonous or not, based perhaps on certain biological features of its leaves. Actually, the example right after this, we're going to see an example with flowers. So we'll see. So let's just say that 1 is going to indicate a poisonous plant and 0 is going to indicate a non-poisonous plant. Again, it's a dummy variable. So I'm forcing my predictions to be between 0 and 1. So suppose for test plant P, I get some value like 0.19, right? So let's just say I do my transformation already. And for some test plant P, I get a value of 0.19, maybe that's about here. So I naturally understand that this is the probability that P is poisonous. So if I want a truly binary prediction, I just round my score appropriately. So if I get a probability of 0.19, I know I'm going to round it down because there's only a 20% chance that this is poisonous, which I know in the grand scheme of things is a pretty big probability if you're trying to really figure that out. But yeah, if I want a truly binary prediction, I'm just going to round my score down. Cool. So how can we fit a line to our dependent variable if its values are already sorted as probabilities? We can use the inverse of the sigmoid function and just set our regression equation to be equal to that. And the inverse of the sigmoid function is a logit function, which looks like this. So if you want to do a transformation from your sigmoid into the straight line again, this is the equation that you have to do. I do not think that the math for this model is very important. So I'm not going to talk too much about it, but there's some derivation of this equation over here, and our linear regression equation is going to look like this. So this equation that we have over here is equivalent to this that we had over here, just in a different form. So therefore, if you want to talk about your coefficients for logistic regression output, which you can get from stats models and scikit-learn as well, you would have to interpret your coefficients like so. So basically, let's say you get, let's just say, I don't know, whether a house is large or small. Okay, let's just say that that is our binary target variable, small house, large house. And let's just say that this is number of bedrooms. And so let's just say we get a coefficient of, I don't know, a coefficient of 5. So that's just saying, the way that you interpret that is that every time you have one more bedroom, this log value is going to go up by 5. And then what the effect is on the actual probability, you would just have to reverse that. Cool. Questions about that? There are going to be there are different ways that you can pull out information from these different models. I would say logistic regression is mostly based on coefficients, and you would have to go through the process of reverse transforming all of these numbers. But yeah, I will say that for this phase, going into the weeds of each model is going to be a little less important, just because we're literally going to talk about a new model every day. But do check out the summary sheet of models that I put on the, I think I put it on the homeroom. If not, it's at the bottom of our homeroom in the resources bin. And there are resources on how you can do that. But cool. Questions at this point, because that's kind of where I end like the theory of logistic regression. Okay. Yeah, there are 2 topics on logistic regression. One of them focuses more on like the math of it all, and then the other topic focuses more on just evaluating any classification model, which is what I'm going to talk about next. And then also, I think it goes into a little bit of MLE as well. All right. Okay, so let's talk about this. We're going to code out a logistic regression just to go through functionally what that looks like. So we have our usual data sets. This should look, let's see, this one is a normalized scalar. This is our logistic regression model, train test split we've seen before. And this is pretty cool. I think I talked about this back in phase 1, but scikit-learn just has a bunch of built-in data sets that we can use to play with. So what I'm going to do here is I'm going to load up this data set, which is actually pretty famous. It's called the iris data set. It is just a data set on like 3 different species of irises, really good for classification. So this is what our data looks like. It's literally just like the length and width of like sepals and petals of the iris flower. And there are 3 classes in our target. There are only 150 data points here, so there's only 50 instances of each flower in this data set. Now, I did talk about how for logistic regression, it has to be binary, but how are we going to tackle this 3-class problem here? So whenever you see your target variable having more than 2 classes instead of binary, I think 3 is called ternary. And then after that, you just say 4-class, 5-class, 6-class classification problem. All of which you can do with the same model. The way it scales is going to be quite similar. So for logistic regression, what's happening when you're doing a ternary problem is instead of just having a probability of it being, 0 or 1, which is very straightforward because to get the probability for the other is just 1 minus the other. For logistic regression, for ternary problems or any more than 3+ classes, the way that logistic regression does it is sort of like a 1 versus all approach. So pretty much you can think of it as not really doing this because it is doing it in parallel, but you can think of it as doing, is it going to be class 0 or not class 0? And it's going to do another version of, is it class 1 or is it not class 1? Is it class 2, not class 2? So the way it scales, because it does say that it has to be a binary problem, the way it scales is just by doing this 1 versus all approach when you have more than 2 classes. Cool. Just some very, very quick EDA on this data set. I will say that for classification problems, it helps to do your EDA in a way that shows differences in your classes. So the whole point of classification problems is to be able to classify your data. In this case, we want to classify our flowers into 0, 1, and 2. So it makes sense for your EDA to go in that direction. So let's just take a look and see, how does sepal length, sepal width, petal length, and petal width differ between the different classes? And you can sort of start to see patterns if it's going to be, if it's an easily classifiable data set, you're going to start to see patterns like this. So for example, you can see that for these 3 species, the sepal lengths are concentrated at different amounts. So for this 0 class, it's around 5, for this 1 class around 6, for this 2 class 6.5. If you can start to see these differences, and the kind of visualization I do recommend for this, especially if you're comparing continuous variables against a categorical outcome. Scatter plots really only work if you have not that many data points. I think a lot of you saw with your last project, they just become like lines like that. So visualizations I do recommend. Box plots are always good. Violin plots is another one that's nice. So do that. So quick EDA, there are only 4 features here, but this is our EDA. And very, very similar process as we did for our scikit-learn linear regression last phase. So we do our train test split. Our X features is basically everything aside from the target. Y is the target, and we do our train test split. So after we do our train test split, oops, let me start from the beginning. Cool. After we do our train test split, we're going to instantiate our logistic regression. What these are, I'm going to talk about in a little bit, but all we have to do is fit our model to our X train and Y train, just like we did for our linear regression, get our predictions for our X train and X test. Oops, I did not run this. There we go. And you can see that for our Y hat, we get a bunch of predictions of 0, 1s, and 2s. And then we can sort of figure out the residuals here. How many were correctly predicted? And because the outcome can only be 0, 1, or 2, all we have to do is see if they match up or not. So here I am taking a look at whether Y train is equal to Y hat train. And we'll see that the number of values correctly predicted is 117 and incorrectly predicted is 3. That's from our train set. And from our test set, we have this 28 correctly predicted, 2 incorrectly predicted. What I want y'all to get out of this section over here is that it's very, very simple to implement a machine learning model. Literally, all I did was instantiate, fit, predict, and I can just get all of these results. And this is going to be a very, very similar process. Sneak preview for the task I'm going to have you do towards the end of this week is just write a function that can automate this process. But yeah, implementing the code, very, very, very simple. This is not what you're going to be doing. There are going to be better ways to show how well your model is doing, which I'm going to talk about right under this. But at this point, questions as I pull up the documentation for logistic regression. Scikit-learn. All right. So I do want to talk about hyperparameters. So we did talk about hyperparameters at the end of last week when we talked about regularization. Remember what we had was that regularization term, which in the equations was lambda, but on scikit-learn is called alpha. Logistic regression actually does have regularization built into it. So if you want to add regularization into your logistic regression model, you can do that. There are a bunch of other things that you can do as well, but most important, I think for this one, for logistic regression, regularization. So you can see here, you can define what penalty you want to give it. L1 and L2, basically we talked about L1 is lasso, L2 is ridge for our linear regression. For logistic regression, they also have L1, L2. There are also some other methods of regularization, which feel free to look up. So here you have what kind of regularization you want. Here, the C parameter, which over here, I think I had as C equals to 1 to the power of 1 times 10 to the power of 12. That is the inverse of regularization strength. So smaller values specify stronger regularization. So I put a pretty big number. So that was very little regularization for that specific model. So if I change this regularization parameter, so let's just say I put, I don't know, 10. I don't know how these are going to change my values, but you can see, yeah, it doesn't really change my values here. Probably because this is a very, very small data set, not very sensitive to changes in regularization. But those are hyperparameters. In the sheet that I sent you all, the model summary, I do note for every model what are important hyperparameters to know. And as we get to the next few models, I will also mention what are the good hyperparameters and how do you think about adjusting those numbers. Okay. Questions at this point? All right. So this section, I'm going to talk about evaluating classification models. Now, these evaluation metrics will apply to pretty much every model we're going to talk about this week as well as next week. So this content is going to be applicable to all of those other models as well. So a couple ways that we can evaluate our classification models. The most visual way, which I do expect to see in your projects that are coming up, confusion matrix. So what is a confusion matrix? It is literally a tabular representation of actual versus predicted values. I'm going to come back to this in a little bit, but scikit-learn has a plot confusion matrix function where you give it your model, your X train, Y train. You can choose whatever colors you want, and it shows you a confusion matrix. I also did this for the test set down here. These are both confusion matrices. Now, how do you read this? Takes a little bit of getting used to, I find. But basically, on one axis, you have the true label, and one axis, you have the predicted label. Now, on the diagonals, where true is equal to predicted, those are what were correctly predicted. Those are the ones that are predicted right. And then anything that isn't on the main diagonal, like for example, you can see that all of these are zeros. So what this says is that no flower that was actually species 0 was incorrectly predicted as 1 or 2. And then this 2 over here is just saying that there are 2 flowers that were actually species 1, but were incorrectly predicted as species 2. Same for this 0.1 over here. There was 1 flower that was species 2, incorrectly predicted as species 1. So that's what a confusion matrix tells you. Very, very visual. It takes a bit of getting used to reading, especially when you have more classes, it gets a little bit more complicated. But the idea is you want to maximize the number of data points that are in the middle here. Something that's pretty good to note about confusion matrix, you can also normalize it. Normalize equals true. I hope that's right. Not normalize. Let's look up the confusion matrix real quick. Plot confusion matrix. If it's not normalized, it is, oh, normalize equal true. Did I spell it wrong? Let's find out. Oh, not Boolean, but like that. Weird. Okay, cool. So that's normalized now. And you can see that out of all of the actually labeled ones, 5% incorrectly as 2. So that's another way that you can interpret. Some people like to have both. Depends on the problem, really. But just so you know, you can get both of these. Okay, so in a confusion matrix, you're just seeing what was predicted correctly, what was predicted incorrectly, and also what each incorrect prediction was supposed to be and what it got wrongly predicted as. So very, very visual. If you're making some sort of model, if you're trying to evaluate your model, you can get a lot of information out of confusion matrix like this. Okay, now back to all of these. From your confusion matrix, and let's just scale down to a binary problem. In a binary confusion matrix, you only have 4 buckets. Now you have your true positive, false negative, false positive, true negatives. This should kind of sound familiar because this is really like where type 1 and type 2 errors kind of come back into here. So from classification models, there are 4 main metrics that we use that are derived from true false positives, true false negatives. So the 4 main metrics that we use are accuracy, recall, precision, and F1 score. These are their formulas. So accuracy is basically anything correctly predicted divided by everything. So basically these 2 true values divided by the sum of everything. Now recall is true positives over true positives, false negatives. So recall actually is basically, you can think about as this number over here, these normalized numbers. So the recall for this over here is 95%. Basically, how many of these actually labeled ones were correctly recalled as label ones? That's how I remember it. There's also precision, which is true positives over true and false positives. And precision is sort of like if you were to normalize it on the other axis, which you cannot do over scikit-learn, unfortunately. But let's just say that we're looking at predicted ones. So out of the predicted ones, you can see that we have two wrong ones here. So the precision would basically be whatever 11 divided by 13 is. So all of the ones that were predicted 1, how many of them were actually 1? So that's precision. And then and then F1 score is basically an average of precision and recall, but it's what is called a harmonic average. So instead of just taking this plus this divided by 2, you're taking a different kind of average that kind of gives you, that is a little bit more strict with your results. You'll see what I mean later. But basically, this is the formula for that. So, okay. All 4 of these I mentioned. We have accuracy, which takes into account both false positive and false negatives. However, can be misleadingly high when there is a very significant class imbalance. Now, class imbalance is something that we haven't spoke about yet. I also will not speak about class imbalance until an office hour, but the materials in your labs, very, very good to read for class imbalance. So yeah, for example, let's just say that you have, let's just say you're trying to detect COVID. Yeah, you're trying to detect COVID. You either have COVID or you don't. However, only 1% of the population has COVID. Let's just say 1% of the population has COVID. Your model, if it just predicts that no one has COVID, will still have a 99% accuracy, because that 1% of people that have COVID, overall, the accuracy is still going to be pretty high. Does that make sense? So accuracy can sometimes be very misleading. Recall and precision are kind of like the flips of each other. Highly sensitive to false negatives, no sensitivity to false positives. Precision, sensitive to false positives, no sensitivity to false negatives. And as we get into examples, we'll sort of see the implication of each one. I would say that whether you focus on recall or precision when you're evaluating your model, think about it in context. What is a positive and what is a negative, and which would you rather incorrectly predict? Because in different scenarios, it's going to be different. And then F1 score, harmonic mean of recall and precision. There are also a couple other metrics. This one, AIC, it's sort of like an R squared. However, we're not going to use this very often for phase 3. This is actually a metric used a lot in time series analysis, which we will get to in phase 4. So don't worry about this for now. But there's also the ROC curve. Now, the ROC curve talks about the trade-off between true positives and false positives. And we'll see some examples of this in a little bit, so I'm not going to explain it right now. Okay, so we've seen confusion matrices, which is the plural matrix. Yeah, confusion matrices, which visually basically will tell you how your model did at classifying. Confusion matrices within scikit-learn, it will automatically scale to however many classes you have. So very, very easy to use. Cool. Next, I want to show you all classification report, because I talked about precision, recall, accuracy, and F1. Classification report will give you all of that. So here, again, I'm getting my train predictions, my train and test predictions, and then I'm printing the classification report, which comes from scikit-learn metrics, for both my train and test set. So this first one is the one for my train set. Second one is for the test set. Same thing for both. So what this is telling me is for each class, what is the precision, recall, and F1? And accuracy is the same overall. So accuracy is actually down here. Accuracy is 97%. For our test set, 93%. So for our class 0, basically everything was correctly predicted. So all the metrics give you a perfect 1 score. Now for our class 1, our precision was 97, recall 95, F1 96. Support is basically how many data points are in that class. And then same for our class 2, the numbers are also not perfect. And that basically is because we have some misclassified data over there. All right. So classification report, also another very useful tool to just give you all the numbers straight off the bat. And each of these numbers, what this recall means, because I know I did say that recall by this is talking about positive versus negative. If you have 3 classes, what is positive, what is negative? Not very clear. So all of these scores down here are also taking a 1 versus all approach. So take note of that. Cool. Now from here, we also have the ROC curve. The ROC curve is basically this curve over here that tells you the trade-off between true and false positives. Basically, it will show you what the good model will basically have this yellow curve over here, And the worst ROC curve you could have is a diagonal line across. And I'll show you the code for that right now. So here I'm importing ROC curve and AUC. AUC is basically area under curve, which is how you determine success. And basically AUC, you can see here that this box has an area of 1 because this goes from 0 to 1. This goes to 0 from 1. You want to maximize your area under the curve. And so therefore you can tell that this blue line has an area under the curve of 0.5. So 0.5 is probably like the worst score you can do. This pink curve, area under the curve, which is basically anything in this region, a little bit higher than 0.5, and the area under the yellow curve, even higher than 0.5. If you have a perfect model, your curve is pretty much going to hug the line like this, and your area will be 1. So that's kind of your goal there. Okay, so the way that you code out AUC and ROC is actually a little bit complicated. So I do want to talk about that because that does come up in some of your labs. But basically what you're going to do is you're going to use a label binarizer. And what a label binarizer does, I'll show you all in a little bit. If I run this, bin, basically it takes your labels and turns them into 3 different columns rather than having 0, 1, and 2. So you have to turn your data into this first. And then when you do your chain test split, you can use your decision function like that. So when you fit this, you can pull out the decision function. And here you have all of your scores, which these numbers look pretty intense. But what this is saying is that for each data point, and this is each test data point, each test data point is associated with these 3 numbers. And these 3 numbers is basically the score for each data point for each class. And they do all add up to 0, sort of like a probability, but probabilities don't go under zeros. But all of these numbers will add up to 0. And basically the classification will go towards whichever has the higher number. So this first test data point is going to be class 2. And that's one step that you have to do. That's one step that you have to do in order to get the ROC curve, especially when you have more than 2 classes in your data set. And from here, there is also a built-in ROC function now for scikit-learn. When I made this notebook, there wasn't. But when I run this over here, oops, I did not run something up here. Okay, there we go. So here you can see that for each class, you get an ROC curve. So you can see that for classes 1 and 3, they're actually both perfect, which is why you can't see both of them. They're both perfect over here. You can sort of see the green here. And for class 2, we have an area of 0.52. And that's sort of related to how in our test set, class 2 was the one that was not being predicted correctly. Cool. So that's just another metric that you can use. But for ROC curves, again, it's also another one versus all approach, which is why each one has its own curve. I will say that most important thing to get out of here is for your classification models, at least have your classification report and your confusion matrix when you're evaluating your model. Something to just keep in your heads as you think about maybe writing a function to do this automatically. Cool. I've linked StatQuest videos for the math behind logistic regression, which is actually very, very elegant in my opinion, but it's pretty in-depth. And then this is something that I'm going to make as optional. You can use this as the data set later on this week when I have you all creating your functions. But this is another data set. It's for credit card default, predicting credit card default using other features. If you want to try testing out your classification models with a data set, feel free to use this one. But cool. I understand that today was a lot of information. We were kind of balancing this new model and also like how do we evaluate this next slew of models that we're going to talk about. So yes, any questions at this point? Okay. If there are no questions at this point, I will say what I would prioritize a little bit more than understanding this model at this very moment is prioritize getting used to how you code out classification models, which is literally these steps of like instantiating your model, fitting and predicting the model, that first. Also your evaluation code. How do you read and understand confusion matrices as well as your classification report? And And at the very end, I would say towards the end of the phase, this next project is going to be you just throwing your data at a bunch of different models. I only ask that you really get in depth for one, maybe two of the models that we're going to talk about. So we're going to talk about, I think, like 9, 10 models in total. So pretty unrealistic to get all of them at this moment right now, but towards the end of the phase, my hope is for you all to at least understand in depth one, maybe two models. All right, any questions before we close out for the day? Cool. Don't forget to respond on the Slack channel, whether you want to work solo or in a group. I'm going to be sending out some group pairs, maybe Thursday, maybe Friday, hopefully before Friday, because Friday is when I'm going to be introducing your project. But yeah, don't forget to do that. Also, don't forget about your blogs. Cool. Where if there's nothing else, Slack me if y'all need anything. If not, I will see y'all tomorrow for a different model. All right. Bye, everybody.